So my name is Andrea Scott, and I want to sort of start by thanking Chris for doing some introduction to the sort of AI kind of world. I'm going to talk a little bit about uncertainty estimates for ice concentration and some open questions in sea ice monitoring. So I'll have a different, I'll start with talking about a little bit about a research project, and then I'll talk about some open questions. Oh, I see, that's better. Okay. So first, let me just start by defining what I mean by ice concentration. So ice concentration is just a fraction of a given spatial area occupied by ice. So in the bottom, in the left there, you see a satellite image. That's an optical image. So the kind of image that you see looking at an airplane. And we have these different size boxes, and there's different sort of bright and dark regions. So they have different levels of ice concentration. So similar to the problem when you look at it in an airplane, the problem with using this kind of data to get ice concentration is that it's obstructed by cloud cover. And so the World Meteorological Organization has recently given some guidance in terms of what they would like to see or what the community needs for ice concentration. So for coastal regions, they're looking for 1 kilometer spatial resolution and 5% uncertainty. And for larger regions, they're looking at 25 kilometer spatial resolution and 10% uncertainty. So if we can't use this kind of data to get the ice concentration, then what kind of data do we use? And so what we often use is this passive microwave data. So passive microwave just means that this is the passive emission of the Earth in the microwave portion of the electromagnetic spectrum. And we have over 40 years of these data that we use to monitor ice concentration. On your left there, you can see just a daily image. So basically, we have these data covering the entire Earth all day, every day. They're also used for a bunch of other variables, essential climate variables like ice, soil moisture, and things like that. And then in your bottom, you see the Arctic sea ice extent, and these are the data that we use to say things like the sea ice extent is decreasing, this is how much it's decreasing by, and that kind of stuff. So basically, the image there, the gray region is the sea ice extent from the 1981 to 2010, and then the colored lines are sort of more recent years. And so we can see, and then the minimum is always typically in September. So we can see that, you know, the minimum has gotten lower, and overall the ice extent in general is getting lower as time goes on. But this data has some uncertainties due to weather. So the data themselves are sensitive to the weather. They're biased for thin ice, and they tend to have a fairly coarse spatial resolution. So, so what I mean by weather, so if you look at your bottom left there, you can see 2 different brightness temperature measurements, so 2 different microwave measurements at 2 different frequencies. In the one in the middle, basically those like yellow regions are effectively cloud moisture, and you can see it looks a lot like the ice, which is at the edge of that red area. So that's like ice at intermediate ice concentration. So those 2 get really easily confused, especially at these kind of higher frequencies where we have this higher spatial resolution. And so while lower frequency methods, like you can see in your bottom right, are kind of like linear in nature, when you start to use the higher frequencies, the methods to get ice concentration become nonlinear. So we looked at this seasonal ice zone off the east coast of Canada, which has fairly thin ice in a damp atmosphere, and it's sort of like what I think of as a sentinel of future change in terms of like what we could see in the Arctic in the future as the ice gets thinner. So to get this nonlinear relationship, we used a neural network, just starting with sort of an older kind of architecture, basically. So just a regular kind of fully connected neural network. We give it an input vector and a training label. The input is propagated through the layers to produce a prediction, which is there then compared with the label, and then that difference is back propagated and the weights are updated. And then this is just repeated until it converges. So it's just like a nonlinear regression method. So now I just wanted to talk for a minute about what I mean by uncertainty for a method like this. So there's 2 different types of uncertainty that we talk about. One is called the epistemic uncertainty, and this uncertainty is what we call due to a lack of knowledge. So we can see those red crosses and those black circles, and we can see that there's a space between them where we don't have data, and there are different lines or different hypotheses that we could use to separate them. So if we had more data, we could probably get a better separation between those 2 classes. On the other hand, the aleatoric uncertainty is what's often people will say this is due to inherently random effects. You could also think of it as happening due to some kind of feature overlap. So for example, that those regions of intermediate ice concentration and the weather kind of overlap. And so we might have high aleatoric uncertainty associated with those regions. So how do we get these into our model? So for the epistemic uncertainty, we used a method called Bayes by Backprop, which basically just means instead of your weights kind of converging to fixed values, you allow them to converge to basically you parameterize them as being drawn from a distribution. And for the aleatoric uncertainty, we used a modified loss function. So basically just taking into account like a Gaussian log likelihood, except allowing that variance sigma to be variable. And then we just got some results that we thought roughly sort of made sense with respect to what we expected to see. So that red line there is your ice extent. You can see that the ice extent hits its maximum in sort of March and April, and then it starts to decrease. So melt onset in this particular region is in May. So when melt onset starts, basically you get a lot of moisture in the snow cover initially, and the brightest temperatures kind of go up and then they go down, and then the ice breaks up. And so that time of year is very, very difficult to know effectively what's going on. So we were definitely expecting to have a high error and high uncertainty at that time of year. And then the epistemic uncertainty, which is given by the height of those green things, is a little bit higher in the summer, maybe because, for example, we don't have a lot of ice, and so it's kind of hard to pin down that sort of boundary between those two. Then spatially, this is some results from April, when the ice concentration has this kind of maximum extent. We can see that the root mean squared error is higher near the ice edge, which is what we roughly expect, and that it's correlated with the aleatoric uncertainty, again, which is what we expect because of that kind of confusion between the weather and the intermediate ice concentration. And in particular, this region is really dynamic. So the ice edge is sort of moving back and forth. And when it does that, because the ocean is relatively warm, there's like a lot of heat transferred. And so there's a lot of moisture in the atmosphere, and that kind of enhances that kind of uncertainty. And then in your bottom right, you can see just over the entire year that trend is fairly persistent. So meaning that the aleatoric uncertainty is always a bit higher for those intermediate ice concentrations than at the water and ice kind of endpoints of 0 and 100%. So just, so our results are roughly consistent with other work that we've done using data from other sensors. And we just wanted to sort of work towards trying to disentangle the impact of ice thickness and atmospheric moisture. So for example, when we look at the projections of sea ice concentration, how much, like, what's sort of our uncertainty envelope? If we start to consider how much the data are dependent on the ice thickness and the moisture. We're also brought into some other applications. And then finally, I'd like to link this with the WMO with their language that they use on uncertainty, and ideally make it sort of more meaningful for that community. So now just a couple minutes about slides and open questions. So basically, we've talked a bit about how reliable it is on concentration data. So fairly reliable, but definitely has some non-small uncertainties that we still have trouble quantifying. And these are more about the ice observation pieces, which are sort of what I work on. We don't know a lot about how thick the ice is, but we have a lot more knowledge now than we did a decade ago. So when I started working on sea ice 10 years ago, we knew very, very little about how thick the ice is. So of course, ice thickness is harder to measure because it's like you can't see it easily from a satellite, right? You need some kind of a signal that can kind of penetrate or that is emitted from like lower in the ice cover. And then knowing like the level to which it penetrates or the level from which it emits is very, very difficult because it depends on snow properties, ice properties, and the signal, like the sensor signal itself. So the same kind of thing goes for snow cover, right? So knowing about snow is important to know about the ice because basically you're solving sort of an inverse problem where you have a satellite measurement and you want to invert it to get these physical properties. But again, I think that's a moving area these days, and there has been really a lot of progress on ice thickness. And then are conditions becoming more hazardous? So people have this idea that with the ice kind of melting, that the Arctic is becoming sort of a little bit more of a benign place, a little bit more livable, and maybe like ships will start going through the Arctic and with no problem. But actually, because the ice is thinning, and storms are kind of tending to increase, storm intensity, it's becoming a little bit more hazardous. And so what information is needed? So just a couple slides about this. So ice hazards, one kind of ice hazard is basically two different types of ice, dynamic ice and pressured ice. So dynamic ice is like regions where the ice cover is changing really rapidly that are very difficult to predict. So for example, in the bottom left there, you can see Hudson Strait. And basically the flow kind of almost forms like a little jet sort of coming out there into the North Atlantic. And that's a very turbulent region. So this is kind of what Francis was talking about this morning. Just there's a lot of uncertainty trying to predict that kind of a flow. This region, Hudson Strait, also in the middle of winter becomes a region of high pressure. So basically, the ice will look totally flat. So you may be like, for example, on a ship leaving a port, ice looks totally flat. It looks like it's going to be smooth, kind of sailing around a ship that has some ice breaking capability. And then the ship becomes completely stuck for days. And that's just because what you can't see is the fact that that ice is under pressure, which has to do with, again, the thermodynamic properties of the ice, the physical properties of the ice. And that's, again, something that we really don't know a lot about. But the people that do the shipping through this region, they would really like to know, because if they get stuck there for a week, it's costing them a lot of money. And it's also potentially very dangerous, right, in terms of environmental impacts. If they have to try to get free, they could have a spill or something like that. It's also like difficult for the local communities because they'll go out on their snowmobiles and like if a ship is stuck and then they don't know what the schedule is, right? And so when the ships go through, like the ship tracks, when they refreeze, they sort of create these little ridges and they have to like kind of get over the ridges. And so it just makes it like another piece of uncertainty for them. And then on the bottom right there, you just see these old ice regions, which is the green and the purple. And again, something that, so normally in the top part of Baffin Bay, there's a strait that gets sort of closed up in the winter. And so the thick ice, the multi-year ice from the Arctic can't come down. But sometimes it doesn't get, sometimes that what are called the ice arches there, they break. And then the ice can be transported downstream and then we lose that ice, right? It basically, it's the old ice that we kind of, we kind of need in the Arctic and we basically lose it. It goes downstream and it effectively eventually melts and causes some problems. And then finally, openings in the ice cover are a hazard. On your right there, you can see these little small openings, which are called plinias. These are tidal plinias, so they're generated from the heat in the tides, and they cause these little upwelling regions of heat. And the communities are finding they're not as predictable as they were in the past. So that's sort of another project that we're working on with some local communities. So that's it. Hope I'm not too much over time. Thank you.
Thank you, Andrea. So, and then